Springfield, Massachusetts, January 7th, 1936. The temperature hovered just above freezing as a 53-year-old immigrant machinist walked through the gates of Springfield Armory for what he believed would be a routine design review. Cantius Garand carried under his arm a leather portfolio containing blueprints for a semi-automatic rifle he had been perfecting for nearly 2 decades. The United States Army had tested prototypes before. They had rejected them before. This morning would be different, not because Garand's design had suddenly achieved perfection, but because the world was running out of time. In Ethiopia, Italian forces were deploying tanks and aircraft against spear-carrying tribesmen, demonstrating the brutal efficiency of modern mechanized warfare. In Spain, civil war was erupting, and it would soon become a testing ground for German and Soviet military technology. In Manchuria, Japanese armies were carving through Chinese territory with a speed that terrified Western military observers. And in Germany, a former corporal named Adolf Hitler had torn up the Treaty of Versailles and begun openly rearming his nation in defiance of every agreement signed after the Great War. The United States Army, still equipped with the bolt-action Model 1903 Springfield rifle designed 33 years earlier, was watching these developments with growing alarm. A bolt-action rifle required a soldier to manually cycle the bolt after each shot, ejecting the spent cartridge and chambering a fresh round. An experienced rifleman could fire perhaps 15 aimed shots per minute. The Germans were developing semi-automatic rifles. The Soviets had fielded the Tokarev SVT-38. Even the Canadians were experimenting with self-loading designs. America, the nation that had invented mass production, that had mechanized agriculture and revolutionized manufacturing, was sending its soldiers into the field with a weapon whose operating principle dated to 1893. The man walking through Springfield Armory's gates that January morning had been trying to change this for half his life. But Jean Garand was not a military officer. He was not a graduate of West Point or MIT. He held no engineering degrees. He spoke English with a thick French-Canadian accent that some army officials found difficult to understand. He had taught himself firearms design through trial and error, through countless failures, through a persistence that bordered on obsession. And he was about to hand the United States military the weapon that would arm 4 million American riflemen, that would serve through 5 wars, and that General George Patton would call the greatest battle implement ever devised. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not in Massachusetts, but in a small farming village in Quebec, Canada. Cantius Garand was born on January 1st, 1888, in the village of Saint-Rémy, about 30 miles south of Montreal. His father was a farmer who struggled to support 11 children on marginal land that produced barely enough to feed the family. By the time Jean reached his 11th birthday in 1899, it was clear the farm could not support all the children. The older boys needed to find work elsewhere. Across the border in the United States, textile mills in New England were hungry for workers. French-Canadian immigrants had been flowing south for decades, forming tight-knit communities in cities like Lowell, Lawrence, and Providence. In 1904, when Jean was 16, his father made arrangements for him to travel to Rhode Island to work in a textile mill. The boy who left Quebec spoke almost no English. He had a 6th-grade education. He owned 1 change of clothes and possessed exactly 0 marketable skills beyond farm work. The textile mills of Rhode Island in 1904 were not pleasant places. Workers, many of them children, operated power looms in buildings filled with cotton dust and deafening noise. Shifts ran 12 hours. Injuries were common. The pay was minimal. But for a farm boy from Quebec who had never seen machinery more complex than a plough, the mills were a revelation. Jean Garand became fascinated by the mechanical systems that powered the looms. During lunch breaks, while other workers rested, the young Canadian would watch the maintenance men repairing broken machines. He studied how gears transferred power, how cams and levers converted rotary motion into reciprocating action, how springs stored and released energy. He began asking questions. The mill foreman noticed the boy's curiosity and offered him a position as a machinist's apprentice. It meant a small pay cut initially, but it meant learning a trade. Garand accepted immediately. For the next 6 years, he learned to operate lathes, milling machines, and drill presses. He learned to read blueprints and to measure tolerances to thousandths of an inch. He learned the properties of different metals, which steels could be hardened through heat treatment, which alloys resisted corrosion. Most importantly, he learned to look at a mechanical problem and visualize a solution. By 1910, Jean Garand was 22 years old and working as a skilled machinist at the Taylor Iron Works in Providence. He was earning enough money to rent a small apartment and to purchase books on mechanical engineering, which he studied at night, teaching himself the mathematics and physics he had never learned in school. And he had developed a new obsession: firearms. The early 20th century was the golden age of firearms development. Magazine-fed bolt-action rifles had revolutionized infantry combat in the 1890s. The Mauser design from Germany set the standard that every military rifle tried to match. But inventors around the world were attempting the next breakthrough, a self-loading rifle that would fire repeatedly without manual cycling. The theoretical advantages were obvious. A semi-automatic rifle would allow soldiers to maintain fire on target without breaking their sight picture or shooting position. Rate of fire would at least double. Wounded soldiers who struggled to operate a bolt could still fire a semi-automatic with one hand. But the engineering challenges were immense. A semi-automatic rifle needed to capture some of the energy from firing and use it to cycle the action, ejecting the spent cartridge and loading a fresh round. This meant the rifle's mechanism had to withstand chamber pressures, exceeding 50,000 pounds per square inch, had to function reliably in mud, sand, rain, and snow, and had to operate at temperatures from -40 to +120 degrees Fahrenheit, and had to do all of this while remaining light enough for a soldier to carry along with ammunition, water, and equipment. Dozens of inventors had tried. Most had failed. Some designs worked on shooting ranges but jammed in field conditions. Others were reliable but weighed 14 pounds or more, too heavy for infantry use. A few worked beautifully but were so complex and expensive that no military could afford to manufacture them in quantity. Jean Garand, a machinist with a 6th-grade education working in a Providence tool shop, looked at this problem and decided he could solve it. He began experimenting in 1912. Using his savings, he purchased a Model 1898 Mauser rifle and began modifying it in his apartment after work. His first attempts were crude. He tried a simple blowback system where the force of the cartridge case moving backward would cycle the action. The rifle exploded during testing, splitting the receiver and nearly killing him. He tried a long recoil system where the barrel and bolt moved backward together. The mechanism was too heavy, and the rifle's accuracy suffered. His breakthrough came from studying an unlikely source: machine guns. The Colt Browning Model 1904 machine gun, which he examined at a National Guard armory, used a gas system. A small hole drilled in the barrel tapped off some of the expanding propellant gas. This gas was directed into a cylinder where it pushed a piston, and the piston operated the action. The system was elegant because it used only enough gas to cycle the mechanism, allowing the rest to accelerate the bullet normally. Garand adapted this principle to a rifle-scale mechanism. He designed a gas trap at the muzzle that would capture gas as it left the barrel. The gas would drive a piston that would unlock and retract the bolt. A spring would return the bolt forward, stripping a fresh cartridge from the magazine and chambering it. The system would reset automatically, ready to fire again the moment the trigger was pulled. On paper, it was brilliant. In practice, it took him years to make it work reliably. By 1915, Garand had a functioning prototype. He took it to a remote quarry outside Providence and fired 200 rounds without a malfunction. He was ecstatic. He wrote to the United States Army's Springfield Armory, describing his invention and requesting an opportunity to demonstrate it. The Army's response was polite but dismissive. They thanked him for his patriotic interest, but explained that the Armory's own engineers were already developing semi-automatic rifles, and they were not accepting submissions from outside inventors. Garand was not discouraged. He continued refining his design, using every spare dollar to purchase materials. And then, in April 1917, the United States entered the Great War. The army suddenly needed every weapon it could get. Factories were mobilized. Production of the Springfield rifle increased from a few thousand per year to millions. And the Ordnance Department began seriously investigating semi-automatic rifle designs, hoping to field them before the war ended. In September 1917, Jean Garand received a letter from Springfield Armory. They were interested in examining his rifle. Could he bring it to Massachusetts for testing? He arrived on October 2nd, carrying his prototype wrapped in canvas. The army testers were impressed. Garand's rifle fired reliably. It was lighter than competing designs. The gas system was simpler than most. They ran it through basic trials and filed a positive report. But the war ended in November 1918 before any semi-automatic rifle could be put into production. The army cancelled most advanced weapons programs. Funding vanished. The Ordnance Department sent Garand a thank you letter and returned his rifle. It appeared that his opportunity had passed. Except the army had noticed something. This French-Canadian machinist, this self-taught designer, had created a rifle that worked better than prototypes designed by their own engineers at Springfield Armory. In January 1919, the Chief of Ordnance sent Garand an unexpected offer. Would he be willing to work at Springfield Armory as a consulting engineer? The position paid $90 per month, about half what Garand was earning as a machinist in Providence. But it offered something money could not buy: access to the finest firearms testing facilities in America, to precision machine tools, to the Army's technical libraries, and to engineers who understood ballistics and metallurgy at levels Garand could only guess at. He accepted immediately. He moved to Springfield, Massachusetts, in February 1919. He was 31 years old, and he had just been given the resources to perfect his semi-automatic rifle. He assumed it would take perhaps 2 years. It would take him 17. The problem was not the basic concept. Garand's gas-operated system worked. The problem was making it work under every possible condition while meeting the Army's increasingly demanding specifications. And those specifications changed constantly as the Ordnance Department's thinking about infantry rifles evolved through the 1920s and early 1930s. First, there was the question of caliber. The Army used .30-06 ammunition, developed in 1906, firing a 150-grain bullet at 2,800 feet per second. This cartridge produced significant recoil and high chamber pressures, making a semi-automatic rifle that could handle these forces reliably proved extraordinarily difficult. Garand spent 1919 and 1920 developing and testing different gas system configurations. He tried gas traps at the muzzle. He experimented with mid-barrel gas ports. He tested different piston lengths, different spring rates, different locking mechanisms. Each variation required building a new prototype, which required machining new parts, which required weeks of work. He would test a configuration, discover a weakness, redesign, and start over. By 1921, he had built and tested 18 different prototypes. None fully satisfied the Army's requirements. Then there was the magazine question. How should the rifle be loaded? The Springfield bolt action used a 5-round stripper clip that loaded cartridges into an internal magazine. This system was proven, and soldiers were trained on it. Garand initially designed his rifle with a similar system, but a semi-automatic rifle fired faster than a bolt action, which meant magazines needed to hold more ammunition. He experimented with 10-round internal magazines, but they made the rifle too long. He tried detachable box magazines like those used on the Browning automatic rifle, but the Army worried that soldiers would lose the magazines in combat. The breakthrough came in 1924. Garand designed an 8-round internal magazine loaded with a special clip called an en bloc clip that held all 8 cartridges together. The entire clip was inserted into the magazine from the top of the open action. When the last round was fired, the empty clip was automatically ejected with a distinctive ping sound, and the action locked open, signaling the shooter to reload. The system was brilliant in its simplicity. A soldier could reload in 3 seconds. The clip weighted only an ounce, and because the clip ejected automatically, there was nothing to lose or keep track of in combat. The Army tested Garand's 8-round clip system in 1925 and approved it immediately. Finally, one aspect of the rifle was settled. The Army conducted extensive trials in 1926 and 1927, comparing Garand's design to competing rifles developed by other inventors. The trials revealed problems. Garand's rifle was still too heavy, weighing over 11 pounds. The gas trap at the muzzle was fragile and could be damaged in field use. The trigger pull was too heavy. Accuracy was acceptable but not exceptional. Garand went back to his workshop. He redesigned the operating rod assembly to reduce weight. He moved the gas port from the muzzle to a position near the chamber, eliminating the fragile gas trap. He refined the trigger mechanism. By 1929, he had a rifle that weighed 9.5 pounds, functioned reliably, and shot accurately. He submitted it for Army trials in January 1930. The trials stretched through 1930 and 1931. The Army tested Garand's rifle alongside designs from John Pedersen, a famous firearms inventor who had designed weapons for Remington. The Pedersen rifle used a different operating system and fired a smaller, lower-powered cartridge. Many ordnance officers favoured the Pedersen design. It was lighter. It produced less recoil. Soldiers could carry more ammunition because the cartridges were smaller. Garand's rifle, firing the powerful .30-06 cartridge, seemed old-fashioned by comparison. Then came the decision that would determine the rifle's fate. In October 1932, Army Chief of Staff Douglas MacArthur intervened personally in the trials. MacArthur had served in France during the Great War. He had seen soldiers die, and he believed absolutely that American rifles needed to fire a full-power cartridge capable of stopping an enemy at long range. The smaller cartridge used by the Pedersen rifle was, in MacArthur's view, inadequate for military service. He ordered that any new rifle must fire the standard .30-06 round. This decision killed the Pedersen rifle program. It also meant Garand's rifle, which had been designed around the .30-06 from the beginning, was now the only serious candidate for adoption. But MacArthur's order created a new problem. The Army wanted a lighter rifle. Garand's design, built to handle, the powerful .30-06 cartridge, was already as light as physics would allow without sacrificing reliability. He could not make it much lighter without using exotic materials that would be too expensive for mass production. The Army established a weight target of 9 pounds, and they wanted the rifle to be no more than 43 inches long. Garand studied his design and realized that every component was already optimized. He could not reduce the receiver length without changing the magazine capacity. He could not shorten the barrel without sacrificing accuracy and velocity. He could not make the operating rod lighter without risking breakage. The only solution was to use different materials. The 1930s saw revolutionary developments in metallurgy. New steel alloys developed for aircraft and automobile manufacturing offered higher strength at lower weight. Garand worked with metallurgists at Springfield Armory to identify alloys that could replace the traditional steels used in firearms. They selected chrome molybdenum steel for high-stress components like the bolt and operating rod. This alloy could handle greater forces than standard steel while weighing less. They used vanadium steel for the barrel, which offered better wear resistance. They specified walnut for the stock instead of heavier woods. By 1933, Garand had reduced the rifle's weight to 9 pounds, 6 ounces, when loaded with 8 rounds. It was 43.6 inches long. The Army accepted these specifications as meeting their requirements. There remained one final hurdle. The rifle needed to pass exhaustive testing to prove it could survive military service. In 1934 and 1935, the Army subjected Garand's rifle to torture tests designed to reveal any weakness. They fired 6,000 rounds through a single rifle without cleaning it. They dropped rifles from heights of 6 feet onto concrete. They buried rifles in sand, soaked them in salt water, froze them in sub-zero temperatures, and then tested whether they would still fire. They subjected rifles to rapid-fire tests until the wood stocks charred from barrel heat. Garand's rifle passed every test. The gas system functioned reliably even when the rifle was fouled with mud. The action continued to cycle even when the rifle was frozen solid. The en-bloc clip system worked flawlessly. Accuracy remained acceptable even after barrels had fired thousands of rounds. In November 1935, the Army Ordnance Department concluded that the rifle designated the T1E2 was ready for adoption. On January 9, 1936, the United States Army officially adopted Jean Garand's semi-automatic rifle as the U.S. rifle, caliber .30, M1. It had taken 17 years from his first attempt in Providence to official adoption. The impossible had become reality, and then came the truly impossible part, building 4 million of them. The Army placed an initial production order for 80,000 rifles in January 1936. Springfield Armory's production planners examined the rifle's blueprints and calculated manufacturing time. Each M1 Garand required 67 precision-machined parts, not counting screws, pins, and clips. The barrel alone required 7 separate machining operations. The receiver, machined from a forged steel block, needed 32 operations. The bolt required heat treatment to specific hardness levels. The operating rod needed precision grinding. The trigger assembly consisted of multiple small parts that had to be fitted by hand. Using Springfield Armory's existing manufacturing methods that had been developed for bolt-action rifles, production planners estimated they could manufacture approximately 50 rifles per day. 50 rifles per day meant 1,000 per month, 12,000 per year. At that rate, producing 80,000 rifles would take nearly 7 years, and the Army was already talking about needing far more. Military planners looking at the situation in Europe and Asia were beginning to suspect that another major war might be coming. If war came, the Army would need not thousands but millions of rifles. Springfield Armory needed to find a way to manufacture the M1 Garand faster than any military rifle had ever been built, and they had approximately 8 months to figure it out. The man who would solve this seemingly impossible manufacturing challenge was not a general or a weapons expert. He was a 52-year-old production engineer named Gilbert Stewart, who had spent 30 years perfecting mass production techniques at Springfield Armory. Stewart had started as a machinist in 1906 and had worked his way up through every department. He understood that building rifles faster was not about working faster. It was about working smarter. Stewart assembled a team of tool designers, metallurgists, and production foremen in March 1936. Their assignment was simple to state and nearly impossible to execute: redesign the entire manufacturing process for the M1 Garand to achieve production rates 10 times higher than current capability. The team's first step was to analyze exactly where time was being consumed. They broke down the manufacture of each component into individual operations and timed how long each operation took using traditional methods. What they discovered shocked even experienced production men. The receiver, the heart of the rifle, started as a forged steel block weighing 6 pounds. Machinists would mount this block in a milling machine and spend 45 minutes cutting the magazine well. Then they would move it to a different machine for drilling the trigger pin holes. Another 30 minutes. Then to another machine for cutting the barrel threads. 20 minutes. Then to another for milling the rear sight mounting surface. Each operation required the machinist to carefully measure, align, and secure the receiver in a different machine. By the time all 32 operations were complete, a single receiver had consumed 14 hours of machine time and had been handled by 8 different machinists. The bolt required similar treatment. Starting as a cylindrical steel forging, it needed the locking lugs cut at precise angles, the firing pin hole drilled perfectly concentric with the bolt body, the cam surface ground to exact specifications, and the extractor groove machined to tolerances of plus or minus 0.02 of an inch. Each operation required skilled machinists using precision equipment. Total time per bolt: 6 hours and 20 minutes. Stewart's team realized that the traditional job shop approach, where skilled machinists moved parts between different machines and performed various operations, was fundamentally wrong for mass production. They needed to think like automobile manufacturers who had already solved similar problems. Henry Ford had revolutionized car manufacturing by creating dedicated production lines where each worker performed one simple operation repeatedly. Stewart decided to apply the same principle to rifle manufacturing. The breakthrough came from a concept called progressive tooling. Instead of moving a receiver to 8 different machines operated by 8 different machinists, Stewart's team designed special fixtures called jigs that would hold the receiver in perfect position for each operation. But here's where it got revolutionary. These jigs were designed so that each one would precisely locate the receiver based on surfaces that had been machined in the previous operation. This meant that once the first operation was performed correctly, every subsequent operation would automatically be in perfect position without any measurement or adjustment by the machinist. They created a receiver production line with 32 stations, one for each machining operation. At Station 1, A worker would place the raw forging into a jig that located it from the flat bottom surface. A milling machine would cut the magazine well, automatically stopping at the correct depth. The worker would remove the receiver and place it in Station 2's jig, which located from the magazine well that had just been cut. Station 2 would drill the trigger pin holes. Station 3 would cut the barrel threads, locating from the previously drilled holes. Each operation built upon the previous one, with no need for skilled machinists to measure or align anything. The genius of this system was that it converted skilled machinist work into semi-skilled operator work. The jigs did the thinking. The fixtures ensured accuracy. Workers needed only to load parts, start the machine, and unload parts. A man who had never seen a rifle before could be trained to operate Station 15 in 2 days. By May 1936, Stewart's team had designed and built progressive tooling for every major M1 Garand component. The results were extraordinary. Receiver machining time dropped from 14 hours to 95 minutes. Bolt machining fell from 6 hours 20 minutes to 48 minutes. Barrel manufacturing, previously a 3-day process involving multiple heat treatments and careful turning operations, was reduced to 11 hours. But progressive tooling alone was not enough. Stewart's next innovation involved the sequence of operations. Traditional gunmaking followed a logical order. Machine all the metal parts first, then heat treat them, then assemble them, then fit the wood stock. This sequence created massive bottlenecks because heat treating required batch processing. You could not heat treat one bolt at a time. You needed to accumulate dozens or hundreds of parts, then run them through furnaces together. This meant parts sat waiting for heat treatment, tying up work in progress inventory. Stewart reorganized the entire production flow using a concept borrowed from railroad scheduling called pipeline manufacturing. Different components would move through production at different speeds, timed so that they all arrived at final assembly at the same moment. Receivers took 95 minutes to machine, but needed 12 hours for heat treatment and cooling. So receivers started their journey through the factory earlier than other parts. Bolts took 48 minutes to machine and 8 hours to heat treat, so they started later. Barrels took 11 hours including drilling, rifling and chamber reaming, so they had their own timeline. The Springfield Armory factory floor was reorganized into parallel production lines, each feeding into a central assembly area. One line produced nothing but receivers, running 3 shifts per day. Another line handled bolts and operating rods. A third line manufactured barrels. Trigger assemblies, which consisted of multiple small parts, had their own sub-assembly line. The wood stocks, requiring careful shaping and finishing, ran on a separate line that started in the carpentry building and ended at the final assembly area. Stewart calculated the timing precisely. If final assembly needed one complete set of parts every 12 minutes to meet production targets, then the receiver line needed to deliver a finished receiver every 12 minutes, the bolt line needed to output every 12 minutes, and so on. He used a concept he called takt time, the German word for rhythm. The entire factory would operate to this rhythm, with each production line synchronized to deliver components at exactly the right moment. The wood stock production was particularly challenging. Walnut blanks arrived at Springfield Armory as rough-cut blocks from lumber suppliers. Traditional stock making was an art form. Skilled craftsmen would carefully shape each stock by hand, ensuring the grain pattern avoided weak points, that the fit against the metal components was precise, and that the finish was smooth. A master stockmaker could complete perhaps 3 stocks per day. Stewart's team mechanized the process ruthlessly. They designed a duplicating lathe that used a master pattern to guide cutting tools. An operator would clamp a rough walnut blank in the machine, start the cycle, and the machine would automatically carve the stock to the correct external shape in 22 minutes. The operator needed no woodworking skill whatsoever. He just loaded blanks and unloaded finished stocks. Inlet cutting, the process of removing wood where metal components would fit, was similarly mechanized. A router following a template would cut the barrel channel, receiver bed, and trigger guard mortise in 14 minutes. What had taken a craftsman hours was reduced to minutes by machines. By July 1936, Springfield Armory's reorganized production lines were operational. The first test run produced 12 complete M1 Garand rifles in one 8-hour shift. This was already a dramatic improvement, but it was nowhere near what would eventually be needed. Stewart's team continued refining the process. They identified and eliminated bottlenecks. They discovered that barrel rifling was slowing down production because Springfield Armory owned only 4 rifling machines, and each barrel took 90 minutes to rifle. The solution was to order 8 additional rifling machines and to run them continuously on 3 shifts. These furnaces operated on fixed cycles, with parts loaded at specific times so that heat-treated components would emerge exactly when the production schedule needed them. Quality control was built into the process rather than inspected afterward. At each station, workers used go, no-go gauges to verify that the operation had been completed correctly. A go gauge would fit into or over a correctly machined part. A no-go gauge, slightly larger or smaller, would not fit a correct part but would fit an out-of-specification part. This system was binary and foolproof. Workers did not need to read micrometers or understand tolerances. They just checked that the go gauge worked and the no-go gauge did not. By October 1936, just 8 months after the M1 Garand's adoption, Springfield Armory was producing 100 rifles per day. This was double the original estimate and represented a remarkable achievement, but it was still not nearly enough. The Army's initial order for 80,000 rifles would take 32 months to complete at this rate, and by late 1936, with Germany openly rearming and Japan expanding its war in China, military planners were beginning to talk about needing not 80,000, but 800,000 M1 Garands. The solution was to bring in additional manufacturers. The Army could not build all the rifles it needed at Springfield Armory alone. They would need to license the design to private contractors who could build parallel production facilities. In November 1936, the Ordnance Department approached Winchester Repeating Arms Company, one of America's premier firearms manufacturers. Winchester examined the M1 Garand blueprints and estimated they could tool up to produce the rifle within 18 months. They proposed building a dedicated factory in New Haven, Connecticut, but Winchester's cost estimate shocked Army procurement officers. The company calculated they would need $8 million to build the factory, purchase machine tools, and develop the necessary tooling and fixtures. This was in 1936 dollars, equivalent to roughly $150 million in today's currency. The Army did not have that kind of funding available. The contract negotiations stalled. Meanwhile, international tensions continued to increase. In July 1937, Japan invaded northern China, beginning what would become the Second Sino-Japanese War. Newsreels showed Japanese soldiers armed with modern semi-automatic rifles overwhelming Chinese troops equipped with outdated bolt actions. American military observers filed alarmed reports. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In August 1937, the Army finally approved funding for Winchester to begin production. Winchester broke ground on their New Haven facility in September. Meanwhile, Springfield Armory continued increasing its own production capacity. By January 1938, Springfield was producing 160 rifles per day. By June 1938, daily production had reached 220 rifles. The production rate was accelerating, but so was the deteriorating world situation. In March 1938, Germany annexed Austria. In September 1938, Germany seized the Sudetenland from Czechoslovakia. In March 1939, Germany occupied the rest of Czechoslovakia. Each international crisis made it more obvious that a major war was coming, and the United States Army, still equipped primarily with bolt-action rifles, was desperately trying to rearm before that war arrived. Winchester's new factory in New Haven came online in August 1939, producing its first M1 Garand rifles. Initial production was slow, as workers learned the manufacturing processes, but by December 1939, Winchester was producing 80 rifles per day and accelerating. Then came September 1st, 1939. Germany invaded Poland. Britain and France declared war on Germany. The Second World War had begun. The United States was officially neutral, but everyone understood that neutrality might not last. President Franklin Roosevelt asked Congress for expanded military funding. The Army received authorization to increase its strength from 200,000 to 500,000 men, and every one of those men would need an M1 Garand. The production crisis intensified. Springfield Armory and Winchester together were producing about 400 rifles per day by early 1940. 400 per day meant 10,000 per month, 120,000 per year. To equip 500,000 soldiers would take more than 4 years at current production rates, and the Army was already planning for potential expansion to 1 million soldiers or more if America entered the war. In May 1940, Germany invaded France. In June 1940, France surrendered. Britain now stood alone against Nazi Germany. Roosevelt and his military advisors began planning for the possibility, even likelihood, that America would eventually be drawn into the conflict. The Army's projected strength was raised to 1.4 million men. The Ordnance Department approached additional contractors. In August 1940, the Harrington and Richardson Arms Company of Worcester, Massachusetts, signed a contract to produce M1 Garands. In September 1940, the International Harvester Company, primarily known for manufacturing farm equipment, agreed to build a rifle production facility in Evansville, Indiana. By early 1941, 4 separate factories were building M1 Garands, but even with multiple contractors, production was not increasing fast enough. The fundamental problem was the rifle's complexity. 67 precision parts, multiple heat treatment operations, tight tolerances, and the need for skilled workers limited how fast the rifles could be manufactured. Jean Garand, who had designed the rifle, now spent his time at Springfield Armory working with production engineers to simplify manufacturing without compromising reliability. He redesigned certain components to eliminate difficult machining operations. The gas cylinder lock, originally a complex part, requiring multiple setups on different machines, was redesigned to allow manufacturing in a single operation. The trigger guard, originally formed from sheet steel through multiple stamping and forming operations, was redesigned as a simple forging that required less processing. These running changes, modifications made during production to improve manufacturability, were carefully tested to ensure they did not affect the rifle's function. Each change required firing tests, endurance tests, and field trials before being approved. But the cumulative effect was significant. By mid-1941, the time required to manufacture a complete M1 Garand had been reduced to approximately 11 hours of total labour time, including all machining, heat treatment, assembly, and inspection. Then came December 7th, 1941, Pearl Harbor. The Japanese surprise attack killed over 2,400 Americans and destroyed much of the Pacific Fleet. The United States declared war, and on Japan. Germany declared war on the United States. America was now fully engaged in a two-front global war, and the army needed to expand to 8 million men as quickly as possible. The M1 Garand went from being an important production program to being an absolute national priority. The War Production Board, the government agency that controlled industrial output, gave M1 Garand production an AA1 rating, the highest priority level. This meant that contractors could requisition steel, machine tools, and labour ahead of almost every other program except aircraft engines and ship propulsion systems. Springfield Armory received authorization to expand its facility and to operate at maximum capacity around the clock. The factory went to 3 shifts, 7 days per week. Daily production at Springfield reached 400 rifles by early 1942, 800 rifles by summer 1942, and 1,000 rifles per day by January 1943. Winchester had similarly expanded, reaching 600 rifles per day by mid-1943. Harrington and Richardson came online with volume production in late 1942. International Harvester's new facility in Evansville began shipping rifles in April 1943. But even these numbers were not enough. The Army was training hundreds of thousands of new soldiers every month. Infantry divisions being organized for deployment to Europe and the Pacific needed rifles immediately. The Ordnance Department instituted a system called controlled substitution, where certain M1 Garand components from different manufacturers could be mixed without compatibility problems. A bolt made by Winchester would function in a receiver made by Springfield Armory. A barrel made by Harrington and Richardson would fit any rifle. This interchangeability was achieved through rigorous enforcement of tolerances and specifications. The system worked because Stewart's progressive tooling concept had been adopted by all contractors. Winchester, Harrington and Richardson, and International Harvester all used jigs and fixtures designed to the same specifications as Springfield Armory. A receiver machined in New Haven was dimensionally identical to a receiver machined in Springfield. This meant the Army could maintain large stocks of spare parts without tracking which manufacturer produced which component. A depot in Australia could stock barrels from multiple contractors and issue them interchangeably to units in the field. By 1943, the M1 Garand production system represented perhaps the most advanced example of mass manufacturing in the world. 4 factories operating simultaneously, producing interchangeable components to tolerances measured in thousandths of an inch, staffed largely by workers who had never built rifles before the war. Production continued to accelerate. By mid-1943, combined output from all contractors reached over 3,000 rifles per day. By early 1944, daily production exceeded 4,000 rifles. The logistics of supplying these factories were staggering. Each M1 Garand required approximately 18 pounds of steel in various forms, forgings, bar stock, and sheet metal. At 4,000 rifles per day, the factories consumed 72,000 pounds of steel daily, just for the rifles themselves. This did not count the steel needed for tooling, fixtures, and replacement machine tools. Walnut for stocks arrived in railroad cars from lumber suppliers in the Midwest. Each factory needed a steady supply of pre-cut blanks. At peak production, over 15,000 walnut blanks were being delivered to the 4 factories every day. The heat treatment operations required enormous amounts of fuel. Each rifle's receiver, bolt, operating rod, and several smaller components needed to be heated to over 1,500 degrees Fahrenheit, held at temperature, then quenched in oil or water, then reheated to lower temperatures for tempering. The furnaces at Springfield Armory alone consumed over 4,000 gallons of fuel oil per day. Quality control remained rigorous despite the high production rates. Every 10th rifle was pulled from the production line and subjected to proof testing, where it was fired with ammunition loaded to pressures 25% higher than normal. If the rifle survived proof testing without damage, the batch of 10 rifles was approved. If it failed, all 10 rifles in that batch were inspected individually to identify the defective component. Random rifles were sent to Aberdeen Proving Ground in Maryland for extensive function testing. These rifles were fired until they malfunctioned or until they reached 6,000 rounds, whichever came first. Failure rates were tracked by factory, by production date, and by specific component. If a pattern emerged indicating a problem with a particular manufacturing process, production would be halted until the issue was corrected. The rifle's reliability in service was remarkable. Field reports from units in combat showed that the M1 Garand functioned reliably under conditions that would have disabled most firearms. Soldiers fighting in North Africa reported that their rifles continued to operate despite exposure to sand and dust. Marines in the Pacific found that the rifles functioned in humid jungle environments where other weapons corroded within days. The semi-automatic action gave American infantry a significant tactical advantage. A squad armed with M1 Garands could produce more sustained firepower than enemy units armed with bolt-action rifles. German soldiers who faced American troops in Italy and France reported that they felt outgunned, that American rifle fire was so rapid and intense it sounded like machine guns. Japanese troops in the Pacific similarly described being overwhelmed by American rifle fire. The M1 Garand's effectiveness in combat validated every year that Jean Garand had spent developing it and every dollar that had been invested in production facilities. By the time production ended in 1945, over 4 million M1 Garand rifles had been manufactured. Springfield Armory had produced approximately 1.6 million. Winchester manufactured nearly 800,000. Harrington and Richardson contributed over 500,000. International Harvester, despite starting production late in the war, manufactured over 300,000. Smaller quantities were produced by other contractors who manufactured components even if they did not assemble complete rifles. 4 million rifles. That number represented an industrial achievement that few nations could have matched. The Soviet Union, with its massive industrial base, produced approximately 12 million Mosin Nagant rifles during the war, but the Mosin Nagant was a simple bolt-action design that had been in production since 1891. The Germans manufactured about 10 million Kar 98K rifles, also a bolt-action design. Britain produced about 4 million Lee Enfield rifles, another bolt-action. The United States was the only nation to equip its entire infantry with semi-automatic rifles as standard issue. Every American soldier, from the beaches of Normandy to the jungles of Guadalcanal, carried a weapon that gave him a fundamental advantage in firepower over his opponents. This was not because American soldiers were better trained or more courageous, though many were both. It was because American industry had solved manufacturing problems that no other nation had successfully addressed. The M1 Garand remained in service long after the Second World War ended. When the Korean War began in June 1950, American soldiers fighting in the frozen mountains of North Korea were still carrying M1 Garands. The rifles functioned flawlessly in temperatures that dropped to 30 below zero. When Chinese troops attacked American positions in massive human wave assaults, the M1 Garand's rapid fire was often the only thing that prevented American units from being overrun. The rifle served through the entire Korean War, from 1950 to 1953. Over 150,000 additional M1 Garands were manufactured during this period as reserves were depleted and rifles wore out from hard use. By the mid-1950s, the Army began developing a replacement for the M1 Garand. The new rifle, which would become the M14, used a similar gas operating system but featured a detachable 20-round magazine and was capable of fully automatic fire. The M14 was adopted in 1957, and the M1 Garand began to be phased out of frontline service. But even then, the rifle did not disappear. National Guard and Reserve units continued to use M1 Garands through the early 1960s. Many rifles were provided to Allied nations through military aid programs. Over 100,000 M1 Garands were given to South Korea. Tens of thousands went to Taiwan, the Philippines, Thailand, and other American allies in Asia. Smaller quantities were provided to European nations, to Latin American militaries, to anyone America wanted to support. The rifle saw combat in dozens of small wars and conflicts through the 1960s and 70s. Some M1 Garands remained in military service into the 1980s, 45 years after their initial adoption. Jean Garand continued working at Springfield Armory through the war and into the 1950s. He never received significant royalties for his rifle design. The Army had paid him small bonuses over the years, totaling perhaps $50,000, but nothing approaching what the rifle's value to the nation would have justified. Some congressional representatives attempted to pass special legislation to award Garand a substantial payment, but the bills never made it through Congress. The designer remained philosophical about this. He had been paid a salary for his work. He had seen his rifle arm the nation's soldiers. That had been his goal from the beginning. He retired from Springfield Armory in January 1953 at age 65. He was honored with a retirement ceremony attended by Army generals and Ordnance Department officials. He gave a brief speech thanking his colleagues and expressing satisfaction that his rifle had served American soldiers well. He moved to Springfield, Massachusetts, where he lived quietly, avoiding publicity. He died on February 16, 1974, at age 86. He was buried in St. Mary's Cemetery in Springfield. His obituary in the Springfield newspaper ran 3 paragraphs and misspelled his middle name. The rifle he designed achieved something extraordinary that goes beyond its technical specifications or its production numbers. The M1 Garand proved that a self-taught immigrant machinist could out-design the weapons experts of the most powerful military in the world. It demonstrated that persistence and dedication could overcome institutional resistance and bureaucratic obstacles, and it showed that American industrial capability, when properly organized and focused, could accomplish manufacturing feats that seemed impossible. The 8 months from adoption to initial mass production was not the result of luck or accident. It was the result of brilliant production engineering by men like Gilbert Stewart, who understood that building things faster required completely rethinking how they were built. The progression from 300 hours to build a bolt-action rifle to 11 hours to build a far more complex semi-automatic rifle was achieved through systematic analysis, creative problem-solving, and the application of mass production principles that had been developed in automobile factories. The story of the M1 Garand's development and production contains lessons that remain relevant. Innovation often comes from unexpected sources. Jean Garand had no formal engineering education, yet he designed a rifle that experts with advanced degrees could not match. Large organizations often resist change, even beneficial change. The Army Ordnance Department opposed semi-automatic rifles for decades despite clear evidence of their advantages. Only the pressure of approaching war forced them to act. Mass production is not about working faster, but about working smarter. Stewart's production team did not speed up traditional manufacturing methods, they replaced them with better methods. Interchangeability at scale requires absolute commitment to standards. The fact that components from 4 different factories could be mixed without compatibility issues was not an accident. It was the result of rigorous specifications and constant quality control. The most important innovations are often not the products themselves, but the processes that make the products possible. The M1 Garand was a remarkable rifle, but the truly remarkable achievement was the system that could produce 4 million of them. Today, M1 Garand rifles are prized by collectors and competitive shooters. The Civilian Marksmanship Program, a government-chartered organization, sells surplus M1 Garands to qualified American citizens. Demand far exceeds supply. Rifles that were manufactured for about $60 in 1943 now sell for over $1,000. Competitive shooters continue to use M1 Garands in matches, praising the rifle's accuracy and reliability. Many consider it the finest battle rifle ever designed. superior even to modern rifles in certain respects. The rifle's historical significance is undeniable. It was the first semi-automatic rifle to be adopted as standard issue by any major military. It armed American forces through the most consequential war in human history. It gave American infantry a tactical advantage that contributed to victory. And it demonstrated that American industry could achieve manufacturing miracles when the nation's survival was at stake. General George S. Patton called the M1 Garand the greatest battle implement ever devised. That assessment came from a man who had commanded armor divisions, who had access to tanks, artillery, and aircraft, yet who believed that a rifle designed by a self-taught Canadian immigrant was the most important weapon in America's arsenal. Patton understood what many historians miss. Wars are won by soldiers, and soldiers need reliable weapons they can trust. The M1 Garand gave American soldiers that weapon. It never jammed at critical moments. It never failed in extreme conditions. It delivered accurate, rapid fire when lives depended on it, and 4 million American riflemen carried it into battle, knowing that their rifle was better than anything the enemy had. That confidence, that knowledge that your weapon was superior, was worth more than any technical specification. It was worth more than debates about barrel length or magazine capacity. It was the intangible advantage that comes from carrying a rifle designed by a man who spent 17 years perfecting every detail, manufactured by a system that produced excellence at scale, and proven in combat from Normandy to Okinawa. The story of how engineers designed the M1 Garand in 8 months and then outfitted 4 million riflemen is ultimately a story about American capability in a moment of supreme national crisis. When the world was burning and democracy's survival was at stake, America's industry rose to meet the challenge. Factories that had never built weapons became producers of the finest military rifles in the world. Workers who had never seen combat armed the men who would win the war, and a Canadian immigrant who had taught himself everything he knew about firearms designed the weapon that would define American infantry combat for a generation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.